Okay, welcome everybody. Today we're happy to have Eric Lescano. He's a postdoc in Wrocław University. Maybe I didn't say it correctly. So he's going to speak about from gauge theory to gravity, classical double copy as a path to higher derivative correction. So Eric, all yours.
Okay, thank you, Lucas, and all the organizers of these very nice seminars. Thank you so much, because I believe that I am starting. This is the first seminar in this new session, so I am very glad to be here. As Lucas said, today we are going to discuss a little bit about classical double copy, particularly in high energy physics. In the last years, double copy has been a very interesting and important topic. Lots of publications and a lot of research in this direction. So hopefully I will try to explain you a little bit about the main ideas about this kind of line of research. I will try to be as much as pedagogical as possible. So I will be glad if you stop me and ask questions. There is no problem about that. We can discuss in between, not necessarily in the end. So please ask the question you need. And let me check if I can move. Yes. So let's start with this program of double copy. Let's try to focus, because I will be distinguishing between double copy and classical double copy. These are two different things. When we talk about double copy, only double, we mean scattering amplitudes related to a gauge theory. Particularly the first discover was about Yang-Mills theory, when we compute amplitudes in Yang-Mills and we cross these amplitudes in a particular way. In this case, we are just writing Yang-Mills cross Yang-Mills. But when we analyze amplitudes in this way, we can artificially construct the amplitudes of the low energy limit of string theory. This means that if we know the amplitudes of Yang-Mills, we can obtain the amplitudes of the metric plus the B field and the dilaton, which these are the fields in the low energy limit, in the supergravity limit, NSNS. And particularly, this interesting relation at the level of the amplitudes can be generalized, as you can see in the last part of this slide. This can be generalized in order to obtain a generic gravitational theory coming from the double copy of two gauge theories. We can cross two different gauge theories. In the particular case where we pick Yang-Mills cross Yang-Mills, we can obtain the low energy limit of string theory. But in general, this formalism is much powerful than that, and we can obtain more general setups. And the main idea behind this kind of double copy procedures, it's related to the dynamics of the closed strings and the open strings. In a very pedagogical way, if we think in open strings that they can attach themselves in order to construct closed strings dynamics, these kind of double copy procedures are decoding this kind or encoding this kind of dynamics, and that is why in the very end we can construct the amplitudes of gravitational theories coming from gauge theories. Particularly, the double copy program was initiated by Bern, Carrasco, and Johansson, and the more general setup, which is the KLT relation, it's due to Kabay, Levenen, and Tai. These were the original people starting this line of research. So recently, in the end of 2021, a classical double copy procedure appeared by a group in Berlin, in Humboldt University. The authors were Olaf Holm, Jaramillo Diaz, and Professor Plewka. Holm and Plewka are still in Humboldt University in Berlin, and they construct a very interesting classical double copy map, meaning that they have an off-shell realization. They start also with Yang-Mills, but at the classical level, they took the classical Yang-Mills Lagrangian. They performed this particular procedure called the classical double copy procedure. In the middle, they obtain a double geometry that I will explain a little bit about this geometry, because in principle, I did my PhD in double field theory, and this stuff is very related to double field theory. So people who knows a little bit about this theory will understand a little bit better this procedure, but I will try to explain in a very general way. So if you don't know about this kind of double geometry or DFT approaches, don't you worry. the main idea here is to try to start with Yang-Mills in flat space at quadratic and cubic order, and following a particular procedure, we are going to obtain the perturbative Lagrangian of NSNS supergravity. Same result as ordinary double copy, but in an off-shell realization. This is a very powerful result from the people of Humboldt, and particularly in this talk, I will try to extend. Depending on the time I have, I will talk about alpha prime corrections as a possible extension of this particular setup, or non-commutativity. So the main question in here is if we can use this classical double copy formalism in order to produce the higher derivative structure of string theory. As perhaps you know, the string theory Lagrangian, when we write the supergravity Lagrangian, we are writing a two derivative Lagrangian, but this Lagrangian has higher derivative corrections. For example, if we focus on Einstein-Hilbert, we know that closed strings produce Einstein-Hilbert dynamics, but also there are other combinations, for example, Riemann square combinations, which correct the theory. And at the end of the day, everybody knows, or probably knows, that a string theory has a UV completion of gravity, has a well-defined gravity at the quantum level, and in some sense is due to this higher tower of corrections coming from the theory. Particularly, these higher derivative corrections came from the integration of the massive modes of the string. I will be not so detailed in this talk, but I will show you a little bit what kind of terms you can find in bosonic and heterotic at the fourth derivative level. And particularly to compute the Lagrangian of a string theory, these 4 derivative terms, 6 derivative terms, and so on, mainly historically was done by scattering amplitudes and beta functions. And particularly these kind of methods are let's say, difficult. That is why in here I am associating scattering amplitudes and beta function to this goal of Maradona, which was a very difficult goal. If we want to reproduce this goal ourselves, it would be very hard on the one hand because we are not football players, but if we would, also it's difficult because it's a very hard way to obtain something, which is the goal. Then in the second goal, in the same worldwide cup, we know that he played this trick, this particular kind of copy trick due to the goalkeeper, and he obtained the same result in a much efficient way. Let's put in these terms, efficient way, and that's it. And particularly, I would like to do the same. I would like to use this classical double copy map. I would like to, instead of starting from Yang-Mills, I would like to start from Yang-Mills plus a higher derivative correction, like gauge correction, gauge Lagrangian with higher derivatives at the flat space, if you want. And then I would like to perform this kind of classical double copy map and obtain a higher derivative structure, hopefully related to string theory. So the outline of the talk is like this. In the first part 0 of the talk, I will review this classical double copy procedure of Hom, Jaramillo, and Plewka. I will be putting a lot of time and energy in this part 0 because in principle, I would like this talk to be pedagogical. So I prefer to talk about this particular procedure for you to learn about it. And then in part 1, I will explain how myself and my collaborators have used this particular setup to construct the alpha prime corrections, particular limit of the alpha prime corrections. And in the very end, if I have time, if not, I will stop in part 1. But if I have time, I will explain you how to obtain also different kind of higher derivative corrections, this time not related to a string theory, but related to non-commutativity, related to this kind of Seiberg-Witten maps and deformations in the gauge theory. This can be done in this kind of setups, and also you can apply the classical double copy procedure to this kind of theory. So in principle, I will try to focus on part 0 and part 1, and if I have time, I will go to part 2. So let's start with a review of the classical double copy procedure. In this moment in the screen, you can see the Yang-Mills Lagrangian. I have a square terms, as you can see very easily. But instead of writing in coordinate space, I am writing in momentum space. This is a very important way to start in order to produce this kind of a classical double copy, because as you can see, we need to factorize somehow our fields, this A square, but also the operators associated to the fields. In this case, if you focus on the Lagrangian, we have the Cartan-Killing metric, this kappa AB. This is the Cartan-Killing metric. We have a K square operator over there, which are just derivatives in momentum space. And also we have this pi mu nu, and this pi mu nu is playing the role of, let's say, the propagator. It's kind of a vertex operator in this case, like a 2-point vertex operator in this way of writing the ordinary Yang-Mills Lagrangian. Of course, in here we are considering just quadratic order, and that's why I don't have the structure constant. But in principle, I am considering non-abelian Yang-Mills, meaning that at the next order, the structure constant will be playing a little bit in here. But so far, we have just this gauge field A, the Yang-Mills field, and also the Cartan-Killing metric. And the main idea here is to try to identify these two ingredients, the field and the Cartan-Killing metric, with other quantities in order to construct a pure gravitational setup. So in principle, we will identify our gauge field with an arbitrary gravitational field. We are calling this one E mu mu bar. We are considering that we are going to a double geometry. We are doubling our coordinates. That is why all my gauge indices, A, B, C, are turning into Greek indices, like a second copy of my space-time. I will have a double geometry. This is a kind of reminiscence to double field theory. And also the Cartan-Killing metric, as you can see, I am associating the Cartan-Killing metric to this 2-point vertex operator in order to have a Yang-Mills cross Yang-Mills form. This is completely artificially because we are at the classical level, but we are trying to mimicking the ordinary double copy. So this is the idea of the authors. And when they impose these kind of identifications, they have this particular Lagrangian in a double geometry. Check that in here I have double momenta. I have K and K bar, meaning that I have two kind of derivatives, ordinary derivative, bar derivative, different derivatives. I have my fundamental fields in this moment are these E fields, and I have these pi operators that particularly I know how to write them. I know how to go back to coordinate position in double geometry because the formula for my pi bar is exactly the same as for my ordinary pi. Particularly an important point, it's a little bit technical, but important, is that we want this Lagrangian to be symmetric under the exchange of K and K bar. And in order to do so, we impose this particular constraint that you have in there, that it's K bar square equal to K square. In this way, the Lagrangian is completely symmetry under the exchange of K and K bar. This a particular thing in order to relate to double field theory and T-duality. I am not going to explain this because it's a lot of time, and I prefer to give you the general idea. But the point is that we can now go to coordinate space and to obtain this Lagrangian that I am showing in this moment. And in principle, this Lagrangian, it's very close to the Lagrangian of ordinary supergravity, NSNS supergravity, but we need to identify the fields in a particular way. This E field, now the symmetric part of the E field is the metric, and the antisymmetric part of this field is the B field. Now we have the degrees of freedom that we want, and also the trace of this field is not the trace, sorry, but this combination that you can see after the Lagrangian, it's given the part of the dilaton and part of the determinant of the metric, very similar to what happens in double field theory. Particularly, this is the old formulation of double field theory where the T-duality is not manifest. This is a technical comment, but somehow it's a little bit important in order to try to obtain like generalization of this method. So somehow we started with Yang-Mills Lagrangian. We impose some identifications to the fields and the Cartan-Killing metrics following the Yang-Mills cross Yang-Mills idea of double copy. This is classical double copy because we are completely off shell at the Lagrangian level. And we obtain this Lagrangian in the double geometry, which can be associated to the ordinary NSNS supergravity at the quadratic order when we identify the fields in the way that you can see in this moment on screen. So in this sense, we start from Yang-Mills and we go to NSNS supergravity, in principle in arbitrary dimensions. The topic about the dimensions, I will be discussing a little bit about this. Give me just a little bit of time in order to discuss this. But now let's try to go to cubic. Let's try to do exactly the same.
I have a question.
Yes.
there's this theorem of Weinberg-Witten that said that you cannot create a graviton from two spin one boson. But this looks like that you are saying somehow that 1 + 1 is 2, and they decompose, and you get the matrix, the field, and the dilaton. So what is like the relation between that theorem and what you are doing in double copy?
This is very closely related. Typically, from the double copy perspective, we always obtain like ordinary supergravity, like the B field is present. You need this B field, and also for this kind of formulation, the B field is important because we have T duality, and the T duality relates the metric and the B field. So in this sense, it's very important. If you want to construct only gravity, like in this kind of a spin 1 plus a spin 1, I am not very sure about which is the direct connection between these kind of approaches, but in principle, this B field, let's say that cannot be turned off that easily. At the end of the day, of course you can, but you lose all the good part about T-dualities, because if you don't have B field, the T-duality is completely trivial. You just exchange your geometry and that's it. Perhaps we can discuss in the end if you want.
Yeah. So how the present of the B field is kind of saying that the Weinberg-Witten theorem is like ruled out from this context?
That I am not sure. That I am not sure. I don't know very well how to combine these two approaches, let's say, from double copy and the Weinberg one. But in principle, if you go in this direction, trying to use this relation between open strings and closed strings, let's say that the string theory is behind this, and that is why you always have this degree of freedom, this B field, apart from your graviton.
Okay, good.
Thank you for the question. So if we want to do the same at cubic order, if we want to exactly do the same procedure, we should factorize somehow. We go to momentum space again. We factorize our A cubic, like you are seeing in this moment. We have our structure constant now. In this particular order, we don't have the Cartan-Killing metric, but we have the structure constant. So the idea is exactly the same as before. We want a Yang-Mills cross Yang-Mills Lagrangian. So we identify the 3-vertex operator in this case, this pi with 3 indices, and we identify our structure constant with this pi. But we in this kind of scenario, we always have like a freedom to put some proportional coefficients. In this case, for example, this structure constant has I/8, for example, in this particular case. We always have this freedom. In order to obtain double field theory in this way, you need to fix coefficients like this. But you will see that when we go to alpha prime corrections, we have more freedom, and there are different possibilities for this kind of coefficients. So far, let's try to use this kind of identification. This is the original identification with a particular number for the coupling, because the gauge coupling is inside this. So if you fix the gauge coupling, then it's equivalent to fix the coefficient. And when you go back to the double geometry structure, to this kind of double coordinate position Lagrangian, again, you obtain this kind of double field theory approach, or NSNS supergravity Lagrangian, when you identify the fields properly and you solve your level matching condition, meaning that your double geometry, in fact, is just ordinary geometry. It's like overlap of two geometries. When you do so, you obtain the NSNS supergravity, but in this case, you need to use the harmonic gauge that you can see here. At the level of double field theory, you need to impose the Siegel gauge in order to everything make sense. And in principle, this is like a limitation that we have in this moment with this formalism at the cubic order. It's not a limitation if you can use the gauge. This gauge is a very reasonable gauge to use. It's compatible with gauge TT. If you go to D = 4 with wave propagation, it's a very strong gauge. You can use it. But let's say that at cubic order, we need to gauge fix somehow. So what I have presented so far is the original idea of the classical double copy, the idea of Olaf, Jaramillo, and Professor Plewka from Humboldt University. And they are still working in this kind of line of research. Together with some collaborators, we did some contributions on this line. So now in this first part of the talk, I will try to explain you how to produce a particular alpha prime correction, which goes like Riemann square. We will focus only on the gravitational ones. And this works with Gabriel Meneses from Rio de Janeiro. I think he's moving to Sao Paulo. I don't know if he's now in Sao Paulo, his permanent position. and also with Ale Rodriguez, who is finishing his PhD in Buenos Aires University. So these are very recent works, and I am very glad that I am sharing these works with you in this moment. Particularly, if we focus on the alpha prime corrections of a string theory, these alpha prime corrections depending on the formulation of the string that you pick, you have different kind of terms. For example, here you can see two lines in this L1. This empty came from Metsaev and Seitlin. They computed this Lagrangian. They computed this Lagrangian from scattering amplitudes at 4-point and 3-point scattering amplitudes. And the terms that we are interested in has the form of Riemann square. As you can see, it has a full contraction of indices. Particularly for bosonic string theory, all the upper line is the alpha prime corrections. You have Riemann square. You have h squared times Riemann. You have h to the fourth. These are the corrections for bosonic. And also, if you want to discuss the correction for heterotic, we haven't worked in that direction, but in heterotic supergravity, the four derivative corrections has the same form as bosonic, but also you have some Chern-Simons contributions. It's this C mu nu rho that you can see in the second line. Particularly, we are going to take A equal B because we want bosonic, so we will focus on the first line. And also, we will focus only on Riemann square. So in principle, I would like to reproduce this Lagrangian, Ricci scalar plus Riemann square. And I would like to reproduce this Lagrangian at quadratic and cubic order coming from the classical double copy perspective, meaning that I would like to obtain Yang-Mills plus a higher derivative theory, a higher derivative Lagrangian, gauge Lagrangian, and after a particular identification of my fields and metrics like Cartan-Killing metrics, structure constant, etc., I would like to obtain this final form of the Lagrangian. It's easier for us if instead of focus on Riemann square, it's easy for us if we focus on Weyl gravity, on C square with this Weyl tensor defined in the ordinary way. It's easier because both Lagrangians are related with field redefinitions, covariant field redefinitions involving the equation of motion of the leading order. Meaning that if we can track a particular higher derivative gauge theory that reproduces Weyl gravity, then we solve the problem. Then we know exactly the alpha prime corrections when the B field is 0, when you don't have three form, let's say, when we have just these Riemann square contributions. So in principle, in this moment, I will put my attention in trying to reproduce Weyl gravity, this C square Lagrangian. In principle, we can try to check the literature and check what people have done in the double copy procedure, in the double copy community, to try to track a kind of Lagrangian structure to use as a test to try to produce this Weyl gravity Lagrangian. So the Lagrangian that we consider together with Gabriel Meneses and Alejandro Rodriguez is this particular Lagrangian. It's a gauge Lagrangian. Now let's try to track the indices because we have these mu nu rho indices, which are space-time. We have the A, B, C, which are our gauge indices in the adjoint representation. And now we have a new set of indices, these alpha, beta, gamma indices. These are also gauge indices, but in the real representation. I am using both representations, adjoint and real, at the same time. This is due to the authors, Johansson, Noble, Mogul, and Teng, that they have created this kind of combination of Lagrangians in D = 6 in order to try to produce Weyl gravity from double copy. We are doing the same. We are keeping D arbitrary, and we are using this proposal in principle to try to obtain Weyl gravity. In this way, if we are successful, we will be obtaining a particular alpha prime correction for bosonic and heterotic, which is the Riemann square contribution. So we have these particular coefficients, A1, A2, A3, A4, A5. When we go to quadratic level, we will have just the first two contributions, the first line of the contribution. And we can follow this procedure of the classical double copy. And we need some extra identifications because we know how to identify the Cartan-Killing metric and the gauge field. But now we have this new phi, this new charge scalar, this phi alpha, and we need to give it a particular identification and also an identification for the Cartan-Killing metric in the real representation. So using these particular identifications, we can try to match with the Weyl gravity Lagrangian. So when we go to coordinate momentum, again, we are in a double geometry setup. We have the same field as before, this E field. This E field, remember that is metric plus B field. And we know that we want Weyl gravity. So in principle, we want the case where E is equal to the ordinary metric. And we would like to fix A1 and A2 in order to obtain Weyl gravity. So the particular combination using an arbitrary gauge, you don't need to fix the gauge in this case. The particular combination depends on the dimension, as you can see in this moment on screen. Let's try to recall, or let's try to learn, if you want, that the Weyl tensor is completely trivial in d equals 3 and in d equals 2. That is why I have roots, and if you want the kind of divergence in d equals 2, but also d equals 3 is a root. So somehow this is a way to verify that you are following a good path, because you need to preserve this d equals 3 root. And in the quadratic order, this is more or less simple to track, but at the cubic order, I am going to present in a few minutes, and you will see that this is a little bit more complicated. But at the end of the day, it's possible to do it. So in this way, we have a way to obtain the alpha prime corrections at the quadratic level for these Riemann square contributions, because it's a little bit technical, but using field redefinitions, we can connect this Yang-Mills plus df theory, if you want, with the kinetic term in the scalar, to the Ricci Einstein-Hilbert plus Riemann square contributions. We can track this. I am not being that technical to show you the field redefinitions. But after reviewing a little bit the cubic order, I can show you a little bit about the form of the Lagrangian and how to connect things. But so far, using this technique, we have started with a higher derivative gauge Lagrangian, df plus kinetic term for the scalar charge scalar field, and we obtain exactly Weyl gravity at the quadratic level. So our ambition now is go to cubic. Robinson, you have a question?
I have a question. This double copy just were like going from Yang-Mills to perturbative gravity, right? It's not like you got the full supergravity stuff.
No,
right?
you have to be around flat space, because you have Yang-Mills in flat space as well. You don't have curve like Yang-Mills. You have like Minkowski metric with your Yang-Mills, so you arrive at the end of the day to a flat space-time.
So it is background dependent in that sense.
Yes, exactly. And try to go beyond this line of direction is also a very good question and a very good topic of research in these days. There are several groups that they are trying to go in this direction, involving this kind of people working in classical double copy.
And the other question is like normally when we talk about higher derivative correction to the Einstein equation, supposedly string theory will give you particular Wilson coefficients, and other theory will give you other stuff. Here you are just matching with the higher correction, or also getting the right Wilson coefficient.
We have in principle we have the correct coefficients to match with the supergravity prescription in general background. It is completely general background. If then you have to have particular, let's say, backgrounds or particular, including any kind of Wilson loops or any kind of extra ingredients in your theory, you can go on. And in principle, there is this matching between the Yang-Mills plus this df theory with supergravity plus alpha prime corrections, but without B field and without dilaton. Particularly, dilaton is not playing a role in this game, because the corrections are just h to the 4, Riemann h squared and Riemann squared. But let's say that B field is not present. So depending on where you want to go, you need to fix this B field equal to 0. You have this, let's say, constraint for the moment.
Nice. Because
also, sorry. But also one of our ambition is to include B field in this game. So more or less, your question is our work in progress. Your questions.
I see. Yeah, because if you don't have the B field, you cannot really distinguish if you are getting like the correction from string theory or for other theory.
Yeah, correct. Yes, totally agree. Yes. Okay, so let me try to show you a little bit what happens when we go to cubic. The thing is a little bit more complicated. Particularly, it's very complicated to extract Weyl gravity at cubic order. It's a very hard computation at the let's say just in the gravitational part without using the double copy, and that is why we were forced to impose some covariant constraints in order to simplify a little bit the model. But still, in this kind of setup, the thing is a little bit complicated. So let me show you a little bit about it. In principle, we need a lot of identifications because we need identification for the structure constant, for the Clebsch-Gordon mixing the representations, for the covariant derivative, meaning that in here in the third line, you have this mapping between the gauge field and the spin connection in the double geometry. And finally, we have this totally symmetric D, that is a totally symmetric structure constant. And we need an identification for this as well. It's a complicated, and this is not unique. This is like a minimal setting of identifications in order to try to capture part of the Weil-gravity Lagrangian. The Weil-gravity Lagrangian, we are imposing some covariant constraints like box H equal to the determinant of H equal to the trace of H equal to 0. This it's completely consistent with in principle, for example, the gauge-Siegel gauge, and also this simplify a lot the form of the Lagrangian. You have to use several partial integrations, but at the end, you can write these particular two coefficients, Fd and Gd. And again, you have this root in D equal 3, which is very important in order to keep in mind that at the end of the day, we are reproducing Weil-gravity, so we need to ensure that when you have D equal 3, everything cancels. So particularly, we have the form of these ones, and with the previous identifications that I showed you, this minimal setup, we can identify the A3, A4, and A6 coefficients in order to match exactly with Weil-gravity in this particular setup. And in this sense, for this particular setup, remember that we don't have B field, but also we have these covariant constraints. But in this setup, we can match with Weil-gravity, with the corrections of Weil-gravity, meaning that in between, remember that in between there is this double geometry or this double field theory appearing. So in between, you have a modification to double field theory, which is not new. When we discovered this, that Yang-Mills plus df square plus d phi square is going to give a modification to double field theory. The modifications to double field theory are already known in the literature, so there is nothing new appearing. This particular modification is called double field theory plus. You need field redefinitions, covariant field redefinitions to make sense, as we were discussing before, in order to obtain Ricci scalar plus Riemann square instead of Weil-gravity plus Einstein-Hilbert. But following this particular Lagrangian in the double field theory geometry that you are seeing in this moment on screen, you can finally make agreement in every sense. You can make agreement between quadratic and cubic gauge theory. And on the other hand, you have like, let's say, double field theory plus, or the alpha prime corrected version of supergravity when you kill the B field. Also, the idea here is to try to relax the covariant constraint that we were using. But the point is that the relaxation of this kind of constraint will give you more general possibilities to the mapping, to this minimal setup of identification that I showed to you. So in principle, I have a notebook in here, and due to the time, I will not be able to talk about non-commutativity. So let me tell you the outlook or the work in progress. We were discussing a little bit recently with Robinson's questions about what the things we can do later. For example, as we were discussing, we need to extend the cubic identifications in order to remove this kind of covariant constraints. On the other hand, we would like to include B field and dilaton, particularly B field is important even for the two derivative case. So B field, for the quadratic case. So for the quadratic case, because you have quadratic contributions. So in principle, B field is interesting. And also if this works nicely at quadratic and cubic order, including B field, and the idea is to try to go to alpha prime square, because the hidden motivation about this line of research is try to capture alpha prime cubic terms that you cannot obtain using ordinary double field theory. Using linear or manifestly invariant geometries, double geometries, there are some particular alpha prime cubic corrections that cannot be obtained with the ordinary methods. And that is why we would like to go beyond the direction of double copy as an alternative approach to obtain this kind of alpha prime corrections. So unfortunately, I don't have the time to try to speak about non-commutativity. You can read the paper if you want. This was a collaboration with Larissa Jonke from Zagreb. And particularly, if you have questions about this and you would like to discuss about non-commutativity, you can just write me an email and we can continue discussing without problems about this topic. So I will stop here and I will address questions if you have. Thank you so much.
Thank you, Eric. But are you sure that you don't want to speak out non-commutative case? Because
we have time.
I mean,
Yeah,
we
you can
were.
go on. Yeah.
We start a little bit late. If we consider this.
That's why. And the
Yeah, but
questions,
there is
the
no
problem.
problem with the time. If you want to go on, there is no problem.
I can speak 5 minutes if you want, because it's not very long story and I have the ingredients to try to show you. I will show you a little bit about what we did with Larissa, because in principle we follow exactly the same idea as before. We try to use this classical double copy, but instead of following this idea about using a new Lagrangian, a higher derivative Lagrangian that we are proposing, we are just using ordinary non-commutative extension of Yang-Mills, particularly for the SUN group. When you want to include this kind of non-commutative corrections, you need to define this star product. This is the main product which defines the non-commutativity, because of course this product doesn't commute. Then you have this particular structure, and this product includes a tower of higher derivative corrections if you want, but not necessarily related to a string theory. In this sense, we are going to perform the double copy of the non-commutative version of Yang-Mills, and we are going to arrive to Einstein-Hilbert plus non-commutative corrections. Particularly to work with non-commutativity requires this beautiful map created by Witten and Seiber, the Seiber-Witten map, which requires a particular expansion, a particular theta expansion for both the fields and the parameters in order to have consistency at the order of the transformations. That is why at the end of the day, our fields also have a star, as you can see here. F mu nu has star, and also we have the corrections coming from the star product. So in principle, if we want to go to follow exactly the same path as before, it's very easy to prove. I am not giving all the details, but it's very easy to prove that at quadratic orders, we have nothing, because in principle, everything is total derivative. So at quadratic level, the theta corrections are just total derivatives. So when you perform this double copy procedure, double copy map, you don't obtain new corrections. In this case, non-commutative corrections. So the important part and the important new physics is coming from the cubic order. These are the first theta corrections which will appear in the theory. So at quadratic order, at all orders in theta, the theory is trivial. So you are forced to go to the cubic order. When you go to the cubic order, you perform exactly as before. You factorize your A field, A cubic, A1, A2, A3. When you go to non-commutativity, you have two possibilities, because you have two kind of structure constants. You have the totally symmetric. The totally symmetric is the D that you are seeing in this moment on screen. And you have also the totally antisymmetric. So in this sense, you have two sources of theta corrections. So in this sense, I am going to show you, we work with a minimal correction, the first non-trivial correction that we can generate, which is cubic and theta square. Why is theta square? If you pay attention in this moment, our pi1, this 3-vertex operator, has a theta inside, and then we are going to identify the D, this structure constant, with another pi, a pi bar. This means that in this double geometry, we will have two kind of products, like the theta product and the theta bar product, two kind of star product, which at the end of the day, when we overlap geometries and identify the geometries, all the thetas will be the same. Theta will be exactly the same as theta bar. They will be identical. Then this will be producing theta square contribution. So the first non-trivial contribution came from cubic order in fields and theta square. So this first contribution has this form, this particular form. As we were discussing, is pi bar 1, pi 1, and the three fields. So from here, we are going to read some corrections to the gravitational setup. Again, we are going to fix B field and dilaton to 0, because for simplicity. And as you can see here, you have this extra and new star product, which is defined exactly in the same way as the ordinary star product, but for the dual coordinates. We have this extra coordinate that appear in the middle when we perform the classical double copy. You have hopefully at this moment you are completely sure that in the middle you have this double geometry. I convince you that you start with Yang-Mills, in this case non-commutative Yang-Mills. At the end you will be arriving to supergravity, but in the middle you have this double geometry, and when you include non-commutativity, this star product also has a doubling, has this bar star product. So there is another source of theta square terms at the cubic order, because you have corrections also for your structure constant. The ordinary FABC structure constant has corrections. The corrections in this case goes like theta square. So in here you have to mix a little bit, because you will be identifying this F with a full 3-vertex operator in the commutative plus the theta correction. And from here you will be reading, like the commutative case, theta square contributions and theta to the 4th contributions, which we will neglect. So from here we have another extra source of theta square corrections in the, if you want, in the double geometry, the DFT action. So the corrections in general, if you want a unified formula, the unified formula for the cubic double field theory action is this formula in here that you can check. We have an arbitrary P coefficient over there because the structure constant totally symmetric, the D, ABC. This one is not fixed by the commutative case, so this introduces a kind of free parameter in the theory. In principle, if we would have a formulation of double field theory with non-commutativity in the non-perturbative setup, we would be able to fix this coefficient. Let's say that this is work in progress in this moment, also with Larissa Jonke. And in general, if we go to coordinate space and we want to analyze a little bit what are these corrections, what is the form of the correction that we have in here, we can work in the gauge TT setup. Remember that in double field theory cubic order, you need the harmonic gauge, and this is a little bit stronger. It's this gauge TT where we are going to find, if you want, some correction to the wave propagation. So using some field redefinitions that you can see in here, that you can neglect Ricci terms, for example, because you have this kind of field redefinitions related to the lowest order Lagrangian. You can find what is the kind of corrections that you have in this setup. And these corrections has the form of theta square, because we are quadratic in theta, but also Riemann cubic. Particularly with this arbitrary coefficient P, this is exactly the Lagrangian that we obtain doing this particular double copying of the non-commutative version of Yang-Mills. And in principle, one can be a little bit worried about, for example, ghost propagation, because if you compute in here now the phase velocity of your wave equation, for example, if you want to go to gravitational waves, you could be a little bit scary about ghost propagation. But the point is that typically in non-commutativity, you take this non-commutativity only on the spatial direction, and this guarantees in general, but also in this particular case, that there is no propagation of unphysical degrees of freedom. And of course, we are truncating the theory. In principle, you have theta corrections at other orders. So in principle, we are giving here the first non-trivial correction to the action. So we have work in progress also in this direction. In principle, we can relax a little bit this gauge TT thing in order to make appear the Ricci tensor. So you can go, for example, to the harmonic gauge or the Donder gauge in order to have new gravitational contributions. Exactly the same as before, you can include B-field and dilaton contributions in this setup. In principle, this is not related to string theory, but you have these two forms appearing. So it would be interesting to study a little bit if there is relation with string theory. There are relations between non-commutativity and string theory, but this is a little bit, this is a very long discussion to have, so I will just say that you can include it and that's it. And finally, as we were saying before, it would be very interesting to have to try to have a construction of a non-commutative double field theory in the unperturbed formulation in terms of generalized metric, generalized fieldbind, and these fields, and try to fix the arbitrary coefficient, this P coefficient. So this is work in progress in this moment with Larissa Jonke. By the way, Larissa is here in Wrocław because she's visiting me in order to try to go in this direction with this particular program. So, so in principle, it's a very active line of research of myself and my collaborator. So now we can finish here. I am open to questions if you have. Thank you so much for your attention.
Okay, thank you, Eric.
Thank you, Eric. Very nice talk.
Thank you, guys. Thank you for inviting me.
Yeah, let me stop the recording and we can start with the more silly questions.